Okay, so let us recall what we did last time. So last time we introduced new object logical quantum mechanics, which was collection of the following data: some super vector space, then we have triple of differentials, u and g plus minus. We had a multiplication, which is graded commutative associative, and some parent g. It is q, g plus minus. They are linear operators. Differentials means linear operators whose Z2 gradient is 1, and they are square to 0. So then this U was an object which took pair of vector spaces. Okay, so it's a Cartesian product of them as manifold, so the tensor product of them in the vector space, and gives us another element. Right?
你可能有演习，有警报，然后现在尽量不要坐电梯。我们一定要下去吗？就没有，就是尽量不要坐电梯。啊，不要坐警报。It said, yeah, there will be some alarm later, just like.
Can we stay in this?
Yeah, we can stay here.
Okay, okay. Okay, so we had this multiplication. That is super commutative and associative. And we have this object G that takes pair of vectors and produces number. Okay, so we are working on a complex number, so it produces element from our base field, which is complex numbers, and that is pairing. And we also want it to be graded symmetric. So if you take homogeneous vectors, like vectors with a pure gradient, and exchange them, then depending on the gradients of this pair of vectors, we will generate some sign. Okay, and then we have a bunch of kind of consistency relations. So we have Leibniz for this pair U with Q, or be more precise, graded version of Leibniz. So then we have some kind of mutual commutation relations between Q and G. So G minus basically anti-commutes this other pair of differentials, while kind of Q and G plus gives us some operator H that we call Hamiltonian, with some additional nice properties that exist to limit t goes to plus infinity with this operator and this limit of the projector to some subspace inside of this V, and with some nice properties that P plus minus acting on this subspace, they act by zero. So that for this property, and then we have like some similar property that this Q and G plus minus, they have certain hermiticity-like property that if I kind of apply G of Q of something, so then it is related to this object with some signs, and it's paired with V. Okay, maybe with plus one. So some of them, like this hermiticity property for Q and G plus minus, they differ by exactly a sign. So that was consistency between differentials, consistency between so we have the two Leibniz, and we have some interesting 7-term relation that is consistency between this mu and G plus minus. So that was consistency between differentials and multiplication. That is consistency between pairing and differential. And the last kind of property, we have the Frobenius structure. That is consistency between kind of multiplication and pairing. So if I do the following thing, so if I take kind of a pair of vectors and multiply them, and then pair with a third vector, so that is kind of element from a third tensor power of V to our complex numbers. So Frobenius property basically requires that this operation from 3 vectors to C is graded symmetric in its argument. So if we exchange arguments, it's like exchanging kind of monomials in a product of graded objects. Okay, that was HEQM, and we have like example of this HEQM, which was, so V was essentially U1 invariant, U1 to the n invariant differential forms of some toric variety. So Q was tensored with some lattice. So Q was essentially differential. So G plus minus were substitution of some vector fields. So we will return to this example later. So here just do it sketchy, and kind of pairing was sort of usual integral for differential forms, and multiplication was essentially a wedge product on differential forms. So we can use kind of differential forms and some natural operations on differential forms to kind of realize all these nice properties. So what we're going to do today? So today we're going to start with some. So we're going to do several things depending on how much time we get or how fast we progress. So first thing is we will define amplitudes in HEQM, and then second thing, we essentially will study some selected properties of amplitudes. And then, kind of depending on time, maybe we will kind of start getting a relation between amplitudes amplitudes is representation for tropical grammophyte invariants. But that's kind of depending on how fast you progress. So, okay. So first thing first is kind of amplitudes. So what is an amplitude? So given given kind of graph gamma, and in our case graph with only 3 valent vertices, and especially marked vertex. So that's kind of the structure that we already saw in context of tropical grammophyte invariants. This kind of graph with revalent vertices, special marked vertex. So that was essentially kind of some decoration of a smooth tropical curve for revalent vertices that we used to describe moduli space, tropical moduli space, and evaluation maps on this tropical. So given this thing, and okay, let me be more careful. Okay, so we will look at the tropical curves with a mark point. So we will allow for 2 types of vertices, 2 and 3 valent vertices, and a collection of states. I will call them psi k. So k goes from 1 to number of leaves, and the number of leaves is the number of one valent vertices of the gamma. So we have this collection of states and collection. So this guys elements of V. So just states, or in physical language, or just vectors in this supervector space, and collection of linear operators. I think we will traditionally call them alpha, because there will be different number of them. So they are essentially linear operators from V to V. And the number of them is the same as the number of 2 valent vertices of gamma. So we have this collection of states, collection of operators. Okay, let me put here in HTQM. So we have HTQM data, E, Q, G plus minus, mu, and G. And then additionally to this standard HTQM data, we add some collection of states, and the number of states is a number of leaves or one vertices for this graph gamma. And then we have collection of operators, 1 operator for each 2 valent vertex. So given all this data, the amplitude, so we will denote amplitude by letter capital A. So we will put subscript gamma to indicate amplitude on what graph we computing, and then here we will put kind of arguments. Let me just check my stations in which order I put them. Okay, I will put operators first. So O1 of set alpha, and here will be set of states, collection of states. And I think sometimes I will kind of put here Q to indicate differential equation here, but I think we will kind of okay. I think for now we are talking about simple, so let's not make things so complicated. Okay, so this thing is okay. First of all, it is a complex number. So we turn all this data into a complex number, and we do it in a following way. So we do the following thing. So we take a tensor product over all this for alpha from 1 to b2 of gamma. Then we take a tensor product of all this psi k from 1 to number of leaves of gamma. So then we take a tensor product. I will explain this in a moment. This thing from okay, in some way this is capital A from 1 to number of terminal edges of gamma. Then we have this multiplication mu. Okay, so here maybe I should do it simpler. So because it is object of the same type, let me just kind of raise it to a tensor power, and here we will raise it to a tensor power of number of 3 valence vertices of gamma minus 1, and then there will be additional object. Okay, let me write it here. So mu3 naught tensor is with this thing, and that mu3 naught is this object. When we talked about Frobenius structures, we kind of define an operation from 3 vector spaces. Okay, and here we do kind of some contraction in tensor algebra according to gamma. So that is a formal definition of amplitude. So for now it looks okay. So for now we kind of missing some details. So K is in physics language is a propagator, and kind of in a proper mathematical language is kind of Q homotopy. So namely, K is an operator defined in the following way. We take an integral from 0 to infinity, dt e to the minus ph, and here we act by g plus. So this thing is a linear operator from b to b. So it is parity odd, because e to the like Hamiltonian itself is an even operator, so exponent of an even operator is an even operator, and then we compose it with g plus, which is odd operator. So therefore here the kind of parity of k would be 1, and the kind of the most interesting property is that if I take anticommutator of q and k, so what I would get? So because of our definition of Hamiltonian as anticommutator of q and g plus, so it's kind of not hard to show that we can use graded Jacobi identity to verify that Hamiltonian commutes with Q. So you can either use graded Jacobi or just explicitly write H as QG plus G plus Q and then kind of multiply by Q to the left and Q to the right and kind of see that the difference is exactly zero, because we either get like Q squared on one of the sides or we get a similar structure QG plus Q, which is obtained by kind of QG plus or G plus Q from Hamiltonian multiplied by Q on the other side. So therefore here, if I perform this anti-commutator, so I can pass Q through this e to the minus ph, and what I would get e to the minus ph, and here we will get commutator Q and G plus, which is again H, and what I get in here is an integral of the total derivative. This kind of extra minus sign, and then this integral equal to the difference of this operator at boundary values, and what we know the following things, that at infinity by construction this operator is a projector operator, so that is kind of where we use condition for existence of a limit, and at t equals 0 it is identity operator, so it is kind of identity on V minus projector to V0, and that is precisely a kind of Q homotopy that kind of contracts our kind of complex. So we have vector space V and Q, so that kind of defines us a complex with a Q as a differential, and then we can imagine having here a kind of subcomplex which is constructed from V0. So V0 is kernel H, but Q can still act non-trivially on V0. So that's why we have here a subcomplex which is V0 and Q. And kind of the important part is that kind of this original complex just splits into a sum of V0 and then some kind of acyclic subcomplex. And this kind of homotopy K, so it performs a contraction from this complex V. So it contracts this acyclic part. So K contracts acyclic part. So in this V acyclic we don't have any cohomologies of Q, so we can just contract it and still get kind of a subcomplex with a differential. Okay, but that was called remark part, so we are not going to use any of this, but that is remark for people who are familiar with some kind of complexes and contraction. So now you can just formally think of this K as a parity odd operator with this nice property that anti-commutator of Q is identity minus P0. So it means that if we are kind of outside of V0, so in this kind of complement of V0, so then anti-commutator of K and Q is 1, and that essentially means that K kind of inverts Q on some subspace. The subspace is complement to. And that's kind of the reason for calling the propagator in physics. So propagator in physics is usually kind of inverse of some kinetic term operator. So in mathematics, kind of inverse of some differential Q, we usually call it Q homotopy. Okay, so that defines K, and Kg minus means we just composing K and G minus, so we get still a linear operator from V2. Okay, so that kind of explains this notation K, And now I need to explain another thing, which is these brackets with gamma. So this thing is a construction in vector algebra okay, according to gamma. Okay, so here let me kind of give a bit more details on this one. So formally it's kind of well-defined construction, but let me give details. So let me start with example. So let us look at kind of gamma, which is okay. Let us start with kind of simplest tree gamma, which kind of contains say single two-valent vertex and two leaves. So we have single two-valent vertex. Let me draw it in this one. So we have this white vertices which are leaves, and this yellow vertex which is two-valent vertex. So V1 of gamma is 2. So we have two vertices, and V2 of gamma is 1. So now, according to my definition, I need to supplement kind of states for each leaf and operator for each two-valent vertex. So here, okay, let's kind of still keep notation. So we have vertex 1, so operator O1, and let me here label them by plus and minus. So here I will have psi plus and psi minus. So that is kind of assignment according to our definition that we need to make to define numbers. So now our amplitude of A gamma, so it depends on O1. So and it depends on this pair of states psi. So now let us kind of follow our formula. Okay, so we don't have this mu3 part because we don't have any three-valent vertices. So this case is kind of a bit special. So there will be okay. So let me. Okay, so little. Okay. So that will be. Yeah, do it like this. So let me. I don't want to. So okay, maybe we should try it. Okay, so let's kind of avoid relation. So let me do it like this. So just kind of to explain the definition, and then we will see how to kind of generalize. So let me take a different tree or different graph with 3 leaves, 1 two-valent vertex and 1 three-valent vertex. So now, according to my rules, okay, so I still need to assign O1 to this vertex, and then I have 3 states. Okay, so psi 1, psi 2, psi 3 equals psi 1. Psi 3 states psi 2, psi 1, psi 2. Okay, so what do we do here? We need to take mu3 0. So then we don't have any leftover three-valent vertices, so there will be no this term. So on this tree, we have this single kind of internal edge. Okay, let me do it step by step. So we have O1, then we have three psi's, psi 1, then psi 2, then psi 3, and we have single internal edge, like this single red internal edge. Use the different colors. So K minus, and this, let me color this operator into yellow. One, and then that's all. So we don't have any other three-valent vertices. Gone. Okay, so how do we produce a number? So let us recall that here psi 1, psi 2, and psi 3, they are elements from V. So we have kind of three elements from V, and that is element of the tensor algebra. So then Kg minus is a linear operator, kind of linear operator from V to V, but we can also treat it as an element of V tensor V star. So it is kind of homomorphism from V to V, and the same as kind of element between V and dual spacing. So here, that will be tensor V star. So then similarly, operator O1 is also operator from V to V, and we can once again treat it as an element V tensor V star. Let me color this vertex. So mu3 0 is an operator from three copies of V to a complex number. Equivalently, we can treat it as an element of V star to the third tensor power. So we kind of treat it in this way that it's some. So okay. Explain. So if I have kind of k of V, I can contract it with some kind of one form. So here contraction is some canonical contraction. So these brackets is just kind of canonical contraction between V and V star. So that is just evaluating this one form on a vector V. So then we can do the following thing. So in order to kind of define or construct this operator K of V, we can do the following thing. So we can evaluate the output for this K of V. We can pair the output for K of V with kind of arbitrary one form alpha, and given these numbers for all alpha and all V, we will have a sort of K of V in some basis. We will have operator K in some basis. So here this thing is what? So action of K on a vector V, so K itself, as we said, so K executed as an element from V tensor V star, and then action on this colors, say blue V. So blue V is another element is an element from V. So we can kind of tensor multiply the V tensor V star for K, then V for this vector V, and for this alpha we can tensor multiply by V star. So alpha is kind of element from a dual space. So this thing, this tensor product is an element of some tensor algebra that is constructed from arbitrary kind of tensor products or arbitrary tensor powers of V and V star. So now let us notice that this element of a tensor algebra has the same kind of number of V's and number of V stars. And what we can do, we have this canonical contraction between V and V star. So therefore, in order to compute this expression, like K of V, K acting on V paired with alpha from this element, so we can perform a kind of two contractions. So in particular, to generate K acting on V, we perform contraction between this red V star and this blue V. And the result, so if I just look at this part of a tensor product, so when we contract this V and V star, we will get an element from V, which is precisely a kind of output or action of K on a vector. And then to get the final number, so we perform another kind of contraction in a tensor algebra, another contraction between V and V star, and that will give us as an output a number. So here we kind of realized an action of K on a vector paired with one form as a contraction in tensor algebra. So we can kind of realize this very same contraction as this kind of brackets gamma. So here let us choose gamma. So in this case, gamma would be the following thing. So we will have two leaves. So kind of some incoming leaf V, outcoming leaf alpha. Let me use the same color. We have leaf V. We have kind of leaf alpha. And we have this red K inserted into valent vertex. So this picture, it basically describes, so if we have kind of directed graph, here we should put directed. So it is graph with some directions on edges. So this directed graph essentially describes a way to perform contraction. So each arrow in this graph will connect like pair of vertices, and on each vertex we either have a leaf or we have kind of some operator that is essentially something like a combination of two arrows. So it is V and V star, and then kind of the arrow that connects kind of two vertices describes a contraction between kind of incoming vector space and kind of outgoing dual vector space. So that was example 0, but let us return to our example 1. So in our example 1, so now we performed the same thing. So we kind of recasted this data that we assigned it to our directed tree. So let me be careful. Let me draw a bigger picture. So we have one second. We have red. We see we have yellow vertex. We have other things. So direction. And here I need to also specify direction. So from here I will specify direction like this. So this plus 3, 0, it kind of takes each up 3 vectors and gets a number. So it has like 3 incoming states which are V and turns it into number. So that is O1 and psi 1, psi 2, psi 3, and this vertex we call it orange. Okay, so we have directed graph, and now we use this directed. So we kind of wrote an object, assign it to vertices of this graph. If you kind of count leaves as one vertex. So then we perform contraction. So let me use. With the green is really okay. So let us start with kind of this edge. So on this edge we have incoming state psi 3, and then it kind of contracts with one of the kind of receiving states on mu3. So let me put here 3 copies. So what we do, we have psi 3, so that is our psi 3. Then we contract this psi 3 with one of the V stars of mu3 zero. It doesn't matter which we use, because we kind of have this Frobenius property that this object is symmetric. So we can choose any of them. So then we perform the same procedure with psi 2. So that is also easy. So we contracted another copy of V with a copy of V star from mu3 zero. Okay, so now we have this other complicated edge. So for this edge, let us also read it from kind of very end from a leaf. So we have psi 1. So psi 1 is another copy of V, and then kind of this psi 1 is contracted with a V star from O1. So we take this V and contract it with V star from this yellow O1. And now what we get this new object, which is red propagator, that stands on each internal edge. And this red propagator is kind of secretly contains another copy of V and V star. So then we take output of this O1. So output of O1 is this vector from this yellow copy of V, and use it as kind of input for this red propagator. So we contract this V from a yellow O1 with a V star from a red propagator. And then the output after applying this red propagator, so we input to so output is in this vector space V, and to get a number we perform the final contraction, which is contracting this output of a red V with input of this orange kind of multiplication of 3 vectors. So this kind of final V star kind of V star component of this mu3 zero. And now we can check that we literally contracted all V stars and all V's, and the result would be just some complex number. So that's kind of how this contraction works. So we just have directions, and then kind of the state that follows along directions is kind of incoming state from V, and then kind of the end of this arrow would be receiving state from V star, and receiving kind of linear form or element from V star, and we perform contraction following this arrows. So in this case, we can actually write down a kind of explicit formula for this expression. So let me erase this example below and kind of write the formula. So to write the formula, let us start with this mu3 zero. So mu3 zero is an object that essentially produces us null. So that's kind of where we would get number. So our amplitude would be equal to mu3 zero evaluated at some 3 vectors. So two out of 3 vectors are kind of easy to compute. Because according to our rule of contraction, so we take psi 3 and psi 2 and just substitute it into mu3 zero. Here will be psi 2 and psi 3. While for this third argument, we need to perform a more complicated procedure. So the third argument, it kind of originates from output of this propagator operator. So it is kg minus applied to something. And now we follow this arrow. So V star was kind of output of this action of yellow operator. So yellow, okay, let me use colors. This kg minus of something, and it is kg minus of output of this yellow operator O1, and then kind of following this yellow operator, the input, input for yellow operator is from a state psi 1. So that is kind of expression for our amplitude. So we expressed it in two different ways. So one way as kind of contraction in a tensor algebra, when we treat these various operations as kind of elements, certain elements of tensor algebra on V and V star. And this another presentation is that we treat them as some kind of operations with vectors or copies of vector space as an input. Then we to psi minus we apply O1, we apply propagator, and then we kind of pair this state with two other states, psi 2 and psi 3. Okay, so kind of this formula is sort of probably quite clear, while this formula is kind of more general and can be used to give a formal definition. With this kind of formula, the best we can hope is some complicated recursive definition, while with this pairing we can give like kind of definition of the object itself, not as a recursion over some subgraphs. Okay, so I hope with these examples it is kind of clear how to compute amplitude given this data.
It is free to select any point to the special 3.3 value.
Okay, so that is kind of a good question. So let us. Okay, I think this kind of label.
If I raise it, I mean, this psi should stay in the image of pi 0, right? This states psi k.
Okay, so couple of things. So for now, the amplitudes are defined on V. So when we will talk about special properties, so when psi's are more special, like elements from V0, so then the amplitudes will have additional nice properties. But the definition works for any states. But kind of when states from V0, the amplitudes are kind of nicer.
Amplitude can also be defined on any.
Yes, on any vector. So let me kind of answer. So that is a very nice question, because like all this directed tree with 2 and 3 valent vertices and special vertex selection looks pretty much like tropical curve with some marked points. And for a tropical curve, we have this nice property for tropical curve. We could use special vertex. And here, let me kind of split this thing into two stages. So kind of shift to another 3 valent vertex, and let me shift to 2 valent vertex. So let me kind of split these cases into two subcases. And let me start with the simpler subcase 1, which is shifting to other 3 valent vertex. Let me start with this kind of innovative example, and then we will kind of formulate a general statement after we understand the example. So let me use my different colors. So I need red, I need orange. Yeah, and I will temporarily use yellow one. So let me look at the situation when my graph gamma is a tree of this type. So once again, I need to supplement directions. So in this situation, kind of let me choose 0. So I have no 2 valent vertices. And now I need to specify 3 valent vertex, like special vertex. So here we kind of agreed that for special vertex, all states should be in kind. So now, and let us look at a very similar graph when we flip this internal red edge. So that is my gamma, and let me put it gamma check. So here orange vertex is here, and yeah, I think I will call it yellow vertex. So and once again, I put the same state psi1, psi2, psi3, psi4. So I put the same states, and I don't have any operators. So let us compute this amplitude on this graph gamma. Okay, so here let us kind of not go over fine details of this tensor algebra. So we can just compute it as series of contractions. So let us kind of look at this vertex, special vertex where mu30 is inserted. 0. Kg minus. So what we have for our amplitude, so we have mu0. So that's kind of our only way of producing number, and then for this mu30 we have 3 incoming edges. So it's 2 kinds of edges which are leaves, psi3 and psi4, and then it is kg minus applied to something, and the input of kg minus is output of this yellow vertex. So it is mu applied to psi1 and psi2. So that is an amplitude computed for a tree gamma. So let us compute an amplitude for tree gamma check. And the only difference is that we performed this change in the special vertex and flipped direction of this red edge to kind of preserve this property that all 3 arrows are incoming for this special. So this thing is once again mu30. And this mu30 now is applied to what? So we have psi1 and psi2. And then we have kg minus of mu applied to psi3 and psi4. So that is kind of good for gamma check. So if you look at them kind of according to their definition, they look quite different. So here we kind of multiply psi1 and psi2 and then apply kg minus and then kind of multiply with psi3 and psi4. So while here we multiply psi3 and psi4, apply kg minus and then substitute the result in this triple pairing with mu30. So there is a kind of natural question whether these 2 amplitudes are equal. So this kind of So when we define a tropical curve, we define a tropical curve up to equivalence relation, and kind of moving this special vertex was one of the kind of one of the structure which was subject to this equivalence relation. So there is natural question whether these two things are equal. And kind of simple lemma is that A gamma of psi exactly equal to A gamma check of psi. So now let us prove proof. So let us kind of prove this lemma in two stages. So one stage, in two steps. So one step would be specific for this choice of gamma and gamma check, while the other stage would be somewhat more general, and we will use this kind of separate other stage as a building block for kind of proving a more general version of this lemma in the form of some proposition. So let's do kind of step one. So step one is we rewrite amplitudes using kind of explicit form that mu3 is a composition of G and mu2. So what we will get with amplitude and gamma, let me just drop in arguments because they're the same. So here what we would have? We would have a pairing G applied to the following object. So because of this Frobenius property, we can kind of freely choose which pair of vectors we kind of multiply with mu and then pair it with. So due to symmetry properties, let me choose a kind of multiplication acting on first two arguments. So it's mu of psi 3, psi 4. And here will be kg minus mu of psi 1, psi 2. And similarly, for gamma check, we can rewrite it in the following way, that it is mu of psi 1, psi 2, and here we'll see kg minus mu of psi 3, psi 4. So essentially, after rewriting our amplitudes in this way, we see that essentially the structure of these two expressions. So these two expressions have the following structure. So it is some pairing of one vector which we'll call v34, which is just product of psi 3 and psi 4. And here it is kg minus applied to another vector v12. While this other amplitude is v12 kg minus v34. And then step 2 of the proof is, I think, what we call kg minus flip. Is kind of a statement that pairing of kg minus pairing of v with kg minus w exactly equals pairing between kg minus v and w. So on a step 1, we kind of rewrote our amplitude as some kind of pairing with kg minus as kind of similar pairings, but with kg minus acting on different arguments. Okay, so now in order to prove this step 2, so let us recall kind of definition of K, and we will use properties of pairing. So we already used. Okay, let me kind of color here which properties we used, because kind of in our definition for HDQM, so we have a lot of properties that seems to be unmotivated. So we kind of used this one to say that K is homotopy, and we used this property a lot to kind of switch to kind of freely choose which pair of vectors we multiply first before pairing with the third one. And now to prove for this step 2, what we will need this kind of properties, kind of how the pairing behaves with respect to action of this operator. So because essentially K, so what is written here is kind of written pairing of V, and here integral over dt from 0 to infinity e to the minus th g plus g minus v. So here I explicitly kind of substituted our definition for K. So now, once again, given that things kind of converge, so I can exchange kind of integral and a pairing. So I will get something like this, e to the minus th g plus g minus w. And now what I can do, I can use this property that if I move g plus or g minus from one argument to another argument, I will generate kind of some sign. So here, what you're going to have, yeah, I think, okay, let me go. There will be several signs. So let me kind of double check to make sure that I didn't mess up these signs. Okay, I think that is somewhat sensitive science. Let me be careful with it. So, okay, so let us recall this property that g plus minus v double that equals to minus 1 to the parity of v, v g plus minus 1. So now we need to use this property twice. So we have g plus, g minus v, and w. Okay, so okay, maybe in my kind of proof, sorry, my proof, I started I computed this right hand side. So let me g. This thing applied to v, directly done, just to be consistent. Okay, so first we need to move kind of this g plus around, and what it will be minus 1 to a parity of this other argument, which is parity of g minus v. And here will be g of g minus v, g plus w. And now we perform the same operation, like moving. Now we will perform a kind of moving g minus from the first argument to the second argument, so it will be minus 1. Okay, so we still have a sign from a motion of g plus, and then we have another sign from moving g minus, so that will be g of v G minus G plus double. So we see when we move first G plus and G minus, so they act in kind of different order on double. And here, let me use this property, the G plus and G minus anti-commute, to get kind of expression that we want. And we have a bunch of signs. And there will be another minus sign, because here we will flip the order G minus G plus acting on double to a G plus G minus acting on double. So now what left is to kind of carefully compute this time factor. So let us notice that according to our definition, so the parity of G minus V is what we call parity of G minus and parity of V. And G minus is by definition an odd operator, so mod Z2, it's 1 plus parity of V. And then when we apply like 1 plus parity of V and we add another parity of V, so then mod Z2 is equal, sorry, mod 2 is equal to 1. Because we have like twice some number which is parity of V. And we have another minus 1 due to the exchange of G plus and G minus. So eventually what we get G of V, G plus, G minus double. So when we flipped G plus and G minus, so we generated no sign. According to our definition of kind of consistency between G plus minus and pairing. And similarly, I think we saw it last time, where I explained what is the motivation for choosing different signs for flipping V and for flipping G plus minus. So it was to have this property that if I flip kind of anti-commutator of Q and G plus, so then there is no sign generated that kind of I can freely move Hamiltonian around and no signs are generated. So it means that I can kind of given. So in a finite dimensional case, when exponent of e to the minus th is just a Taylor series in H, so when this thing is just sum of minus th to the power k divided by k factorial, so I first expand it into sum and then perform this flipping of a Hamiltonian k times. So at least in finite dimensional case, I can kind of freely flip e to the minus th. And nothing. So the story is kind of trickier in a case when we are working in infinite dimensional case, when e to the minus th is not a sum of this series, but rather solution of some differential equation. So that kind of require a separate argument to ensure this form. But for now, let us kind of pretend that our finite dimensional proof still holds in kind of infinite dimensional case where we really want to apply. So therefore these two formulas. So first is this kind of moving G plus minus from a first argument to a second argument without a sign, and moving e to the minus th from a first argument to second argument gives us no sign. And given that we can commute this integration over dt and a pairing, so first we put integration outside, we get this expression. So then we kind of use these two properties to. So e to the minus th commutes with both G plus and G minus, so it doesn't matter in which order we write it. So we use these properties to move all these three operators to the second argument without any extra sign. And then we recover the integral. And at the final stage, we once again commute integral and a pairing. So we can bring integral inside, and then we will get kind of g of v kg minus 1. And that kind of completes the proof of a second step, which is kg minus flip, that just kind of using definition of K and using these sign properties of kind of commuting G plus minus and Hamiltonian through a pairing, we arrive into this nice property that if you have pairing of vector v and kg minus of some other vector, that is exactly equal to pairing of kg minus with the first vector and the second vector term. And this kg minus flip is essentially like flipping this direction of this arrow, because direction of this arrow tells us who is a kind of argument of this kg minus. Like in this picture, kg minus was acting on this state which is product of psi1 and psi2, while in this picture kg minus was acting on the state psi3 and psi4. So now in a more general situation, let me read this part. It's really technical. So this example for the simplest kind of amplitude where we have a kind of same type of a tree, but kind of colored in a different way. So with this kind of different direction of internal arrow and different mu2, mu and mu3 vertices. So proposition that we can really change special vertex without changing the corresponding amplitude. So it means the following, that we have some graph gamma. Okay, let's kind of bring up. And we, so that is our gamma, and let's say we have orange vertex here, and some kind of yellow vertex here. So that is our gamma, and let's say gamma check, where we draw a same tree, but now it is kind of decorated or colored in a different way. So let's say we choose orange, so all the vectors. And say we want to put orange vertex here, and all other vertices are yellow vertices. So in the case of a tree, there always will be like a unique direction if we choose all our kind of leaves to be directed inside. So there will be like unique direction such that it preserves this property that that for this special vertex all lines are independent. So let me draw the propagator by red. And now, kind of what we do the following thing, that to move our kind of special vertex from original position to a final position, so we can so on a tree, gamma, we have unique path between, let's say, VC and VC check. So VC was our original vertex, which is labeled as orange vertex, and then VC check is kind of this vertex in kind of colored gamma. Directed, so gamma is kind of underlying tree that is common for gamma and gamma check. So what we do, so we have unique path. So that is our unique path gamma. that connects these two vertices. And then path gamma is essentially a collection of some finite, and in this case, finite number of internal edges. So gamma traverses these three internal edges, let me call them 1, 2, and 3. And then to kind of, so to show that amplitudes on this graph gamma and gamma check are equal, so all we need to do, we need to perform this kg minus flip exactly 3 times. So first we perform kg minus flip. So these two are equal q to kg minus flip performed for each internal edge along the path gamma. Path gamma is some collection of internal edges, and then we just perform this flip exactly 3 times. So first we perform this flip, so that essentially like exchanges this orange vertex and this yellow vertex, and then we perform flip 1 more time, that will exchange this vertex with this vertex, and so on. And on the third flip, we will get like all these 3 red internal arrows flipped, and we reached this other graph gamma check, which is kind of has a different specially marked value. So I think that was kind of extensive answer for your question, and now we really need to make a break. Just go get into it. So now it's this 11:13. So 11:13. Yeah, let's make 10 minute break. So to 11:20. Okay, maybe quick question before the break.
So we will also prove the second case, shift to as well.
Yeah, so for a second case, we need to be more careful. Like you can probably realize that that kind of when we did this, the first thing can kind of decompose it +3 vertex into pairing and multiplication. We can kind of imagine the same situation that we can introduce a new type of 2-valent vertex, which is composition of yellow operator action and a pairing G. So for ordinary 2-valent vertex, so I think we draw it in yellow, we kind of had one incoming state and one outgoing state. And that was kind of corresponding operator from V2. So we can introduce special 2-valent vertex when we have, okay, so let me call it O0. So that will take a pair of vectors and produce a complex number. And this O0 is nothing but a composition of pairing G and operator O. And this special vertex, okay, I should draw in orange. So we'll have 2 incoming states. So 2 incoming states would produce us a number. So given this extension for a definition that I gave for amplitude, so in that definition I kind of secretly use the special vertices as 3-valent. But we can kind of extend this definition for allowed special vertices to be 2-valent vertices, and then we can perform a kind of kg minus flip on a path between, say, one special vertex to another special vertex. Once again, working on a tree, such path is unique, and it is kind of unique path regardless whether it is path between 2-valent vertices or 2 and 3-valent vertices. So yes, kind of part two is sort of like a straightforward generalization if we adopt this additional definition for a special one.
Yes, the like the mu 30 is like multiplication of two states and the pairing with another state.
Yes.
But mu is like so we can the proof here is like we can change mu to be mu 30.
Not only so in a proof we have like two steps. So first we decompose mu30 and into pairing and mu, and then we kind of move the pairing part around. So we used kg minus flip to move kind of g around.
Yeah.
So we kind of move at a vertex where all arrows are incoming from one point on the graph, from one vertex on the graph to another vertex on the graph. So essentially first we decompose mu30 into mu and g, and then by doing kg minus flips, we essentially move this pairing g like propagated on a tree to some other vertex, and then we once again final composition of g and some mu. We will call a new mu30, and that would correspond to kind of choosing a different special vertex.
Yeah. It's like if mu3 and mu30 can decide each other, it's like do we need to assume V is finite? Because it's like we use the pairing G to decide whether the image of mu.
So from algebraic point of view, so we just need this property that mu30 is kind of has this Frobenius property that we can freely choose which pair of vectors we multiply first. So as long as this Frobenius property holds in infinite dimensional case, we are fine. So what we care is this algebraic property. So in finite dimensional case, it's probably easier to verify. But if we have some natural objects like G is some integral of a wedge product of differential forms, and mu is just another wedge product. So this mu30 is just integral of a triple wedge product. So then using kind of proper differential forms such that integral of this product of forms makes sense. So then we have this example of mu30 on infinite dimensional space that obeys this kind of Frobenius property. So I think that's kind of how things work. So as long as you satisfy this Frobenius property, then you just use it to formally perform an operations on kind of amplitudes.
I mean, if we have a mu30 here, can we recover a mu? I mean, here you have a mu, then you can define this mu30.
Okay, so to recover mu from mu30, you need an additional property that your pairing is non-degenerate. So you see that here I kind of never assumed anything about pairing being non-degenerate. I think at some later stages we will assume that the pairing is non-degenerate. But for now we are working in somewhat more general construction, and if pairing is degenerate, then we can't quite kind of undo this G in this composition to get a mu from mu30. Okay, so let us have a break. So it should be 10 minutes. Okay, so now we kind of continue studying some nice properties of amplitudes. So we already discussed one property, is that we can really choose a special vertex without changing the amplitude itself. So to write down another pair of two nice properties, let us introduce a kind of new object. So for collection of states, once again, psi k just states in V in HTTP V T plus minus V. Correlation function. Or to be more precise, endpoint correlation function. So K here runs from one to n. We have n states, and we define an object endpoint correlation function. So here I will put label Q, kind of label HTTP. So this thing is defined in the following way. So we take sum over all trees, and here over all trees with exactly n leaves. And here we do the following thing. So we divide by the size of automorphism group of each of these trees, and here we kind of multiply it by amplitude. Yeah, need to sigma 1 times sigma of f. And we also perform a summation over different, yeah, let's put it here, summation over all possible permutations of this n labels. Yeah, so that is kind of our definition for a correlation function. So you can recall that that we kind of presented Gromov-Witten invariance as some kind of correlation function for n cycles, and in kind of on a B side of our mirror we have correlation functions on Landau-Ginzburg-Saito model. So it is very natural to kind of introduce this concept of correlation function on the level of HTQM, such that, as we will see in I think on the next lecture, that for kind of A-type HTQM, which is this HTQM, this correlation function would be equal to a certain tropical Gromov-Witten invariant, and after some resummation, there will be similar type of correlation function that would be eventually equal to correlation function in Landau-Ginzburg-Saito. So that is kind of preparational definition that we defined some correlation function in terms of this HTQM construction. So let me give you a few examples. So here let's say n is bigger or equal to 3. So that is our usual limitation, usual assumption that when we work with either Landau-Ginzburg-Saito model, that we start with a 3-point function and define higher point correlation function recursively, and then the same thing when we talk about Gromov-Witten invariance for genus 0, we kind of also want to start with the 3 marked points to ensure that our moduli space kind of makes sense for any degree, including degree 0. Okay, so example, so simplest n equals to 3. So in case of n equals to 3, there is unique gamma with 3 leaves, and this gamma is just this star-shaped tree. So what is the kind of size of automorphism group of this gamma? So we can freely kind of flip any kind of pair of edges. So that gives us automorphism group of the size of 6 factorial. So essentially automorphism group is just symmetry group of 3 elements. So we can kind of relabel these edges in any way we want.
Do we assume gamma doesn't contain 2 valent vertices?
Yeah, so here there are no 2-valent vertices, so here gamma only has, okay, so it's a tree with only 3-valent vertices. Good point. With only 3-valent vertices. So it's like a tropical curve without any mark point. Okay, so then correlation function psi 1, psi 2, psi 3. is what? So we have only single gamma. So the first sum is trivial, and here we divide by size of automorphism of gamma, which is S3, so we divide by 6. And here we need to perform a sum over 6 different permutations, and here will be amplitude on this tree. Let me just draw it like this. Sigma of 1, size sigma of 2, size sigma of 3. So let us recall what the amplitude on this tree. So on this tree we have single 3-valent vertex. So that gives us essentially no choice for this vertex. We perform a pairing, and this amplitude itself is just use the zeros evaluated on kind of string size. And kind of by construction, by this Frobenius property, this mu3 is kind of properly graded symmetric. So it means that all 6 terms are the same. So due to Frobenius property, all 6 terms are the same. Are equal. So therefore this amplitude simplifies. So we have exactly kind of 1 over 3 factorial. So 1 over 6 and 6 identical terms. So therefore this 3-point function is simply mu3 product of these 3 things.
You state that the Frobenius property is like gradient symmetry.
Yes.
So is there any grading being used?
Yes. Okay. Good point. Yeah, you are right. So let me. Yeah, I think here I kind of made a secret assumption. Yeah. So here all these are even states. So all these are even states. So there is no kind of extra sign when we compute them. Yeah, I think it's a good point. So if they have different parities, then we wouldn't have this problem. So assuming that all states are even, so we have this nice simple formula for this 3-point correlation function. So kind of next example is a case when n equals to 4. So in this situation, once again, so we have unique gamma with 4 leaves, and this unique gamma is this tree of this shape. So once again, here now we have like different choices for placing orange vertex, but once again we studied this, we proved this kind of property that it doesn't matter where we choose this 3-valent vertex, all amplitudes would be the same, so they only depend on the order kind of which we assign our states. Okay, so what about symmetry group, automorphism group of this gamma? Let me call it gamma 4. So what is the automorphism group? So what we can do, we can freely exchange this pair of edges. So if we exchange this pair of edges, the picture doesn't change, and we can independently exchange this pair of edges. So that gives us kind of 2 factor, another Z2 factor, and also we can kind of reflect under this vertical line, and also nothing changes, so that gives us another Z2 factor. So the size of automorphism group is 2 by 2 by 2, which is 8. Okay, so let us recall what is the size of S4. So S4 is permutation group of 4 elements, and the size is 4 factorial, which is 24. So therefore here in the sum we will have 24 terms. So for a different label. But let us notice if we perform computation, say 1 and 2, and that kind of leaves 3 and 4 the same, the amplitude does not change. And so that is this property that an amplitude essentially in kind of explicit formula A of gamma is something like mu3 so G of mu of psi 1, psi 2. Okay, for this one, say kg minus mu. For this particular key. Psi 3, psi 4, and here kg minus psi 1, psi 2. And once again, we will assume that both psi's are even. So in this case, the kind of graded symmetry on mu basically tells us that mu of psi 1, psi 2 is mu of psi 2, psi 1. So therefore, if I perform a kind of permutation of 1 and 2 or 3 and 4, kind of the amplitude doesn't change. Furthermore, the kg minus slip basically tells us that if I perform permutation of pairs 1 and 2 and 3 and 4, the amplitude also doesn't change. So therefore, that gives us essentially 3 distinct kind of class conjugacy classes in this form, and each class has kind of symmetry group Z2 cross Z2 cross Z2. And these 3 and therefore what we will have like 3 distinct values for amplitudes. And these 3 distinct values we can just kind of draw them. So it is essentially 3 different ways of choosing kind of pair of elements out of 4 elements, like up to bottom. So that is essentially a kind of, if we fix the first leg to be 1, so all these expressions will be labeled by 3 possible choices for this second leg. So that will be 4 and 2. So that are exactly a kind of assignment of this state that give us 3 inequivalent amplitudes for this tree. So all other assignments, like if I flip like some states, then each of like any other reassignment would be equal to one of these 3 reassignments. And for each of these assignments, there will be exactly this 2 cubed 8 reassignments that are equal to each other. And therefore here, for kind of 4-point correlation function, so we have this one factor of 1/8 due to automorphism group of gamma. But then we will have factor of 8 because each of these inequivalent kind of assignment of states will contribute exactly 8 times. And here we will have the 3 terms that are drawn on a picture. So A1, A2, and A3. And that is kind of A1, A2, and A3. And that this kind of sum is also quite famous in kind of particle physics. So in particle physics, like these 3 kind of labels, they traditionally called S, T, and Q channels. Remark that this kind of three inequivalent amplitudes. They have special names, ST and U channels in kind of scattering theory, where we have kind of scattering two particles into two particles. Okay, and similarly, you can kind of construct higher point amplitudes. So they kind of work in a similar way. And I think gamma 6, like 6 points, is the first situation when you will have a kind of non-unique tree with 6 leaves. So there will be two distinct types, and then they will have different automorphism groups. So therefore you need to kind of treat them separately, and you will get kind of more complicated expression. Okay, so what is the point of introducing these correlation functions other than preparation for chromophilia? Because these correlation functions, they have nice properties. Okay, shouldn't have a risk, but let me kind of write it again. So let me kind of start with a simple lemma that given psi k such that q times psi k is 0, so psi k are q closed, k 1, 2, and 3. So it's kind of being q closed. Yeah, okay, so it doesn't quite imply that they are from V0, but they are somewhat special states. So states from V that are Q closed. So given this thing, the 3-point amplitude, the 3-point function, okay, maybe I should formulate. Let me formulate or in kind of answer. The 3-point function only depends on Q cohomology classes of psi k. So namely, for psi q such that q psi k equal to 0 and another state chi, the following property holds that psi alpha psi beta q chi equal to 0. So dependence only on cohomology classes means that for Q closed states, I can freely shift my Q closed state by Q exact thing, and the answer doesn't change. So and this 3-point function is precisely the change of the answer. So amplitude so correlation function by our construction is kind of linear in all arguments. So therefore shift of one of the argument by Q exact thing will be a sum of 2 amplitudes, original amplitude plus amplitude with kind of one of the objects being Q exact. So here we assume that parity of chi equal to 1. So just to get the same type of amplitude with 3 arguments all being states of parity 0. So the proof is kind of rather straightforward. So what we do, we have explicit formula for this amplitude. So it's psi alpha, psi beta, and q of chi. And then we kind of recall that mu3 0 is a pairing combined with multiplication. So let me choose multiplication to act on psi alpha and psi beta. And here we have q chi. And then we use our property that we can kind of move q to a different argument of a pairing at the price of a sign. And here, once again, okay, so I don't really care about sign at this point, so let me put plus minus, so that will be g of Q applied to mu of psi alpha, psi beta, and then pair it with chi. And here we use the property Leibniz rule for Q, that Q applied to multiplication is kind of Q applied to a first argument. And now all psi's are even, so there will be all signs, all relative signs will be plus. That will be Q of psi alpha, Q of psi alpha multiplied with Q of psi beta. And then in kind of final stage, we noticing that at each of the terms we have Q acting on a state, and that is by definition is zero, by assumption is zero. So therefore sum of these two terms is zero, so between the two term is zero, and if it is zero, then this term is zero, so this thing is zero. So we completed the proof of our lemma. So this proof has a kind of possible graphical realization, which is kind of somewhat useful, and maybe I will just use it for the sake of saving time. So let me kind of draw a graphical proof of this kind. So let me kind of put an additional label Q to kind of indicate that we apply operator Q. So this is kind of chi, this is psi 1 and psi 2. And then what we can do, we can kind of move this Q to this trivalent vertex, and then as we move Q, due to Leibniz property, we will get kind of sum of two graphs where Q now is assigned to other lexi psi 1 and psi 2. So that is essentially kind of graphical presentation of Leibniz rule that if I move Q through a trivalent vertex, it kind of splits into Q acting on each of the outgoing edges. And then kind of when Q is assigned to kind of semi-infinite edge or leaf, so it essentially annihilates it. So here we kind of move it through this vertex, annihilate leaves, and it got here. Okay, so that was kind of nice and simple property for this thing that that these correlation functions, they are nice in a sense that they only depend on cohomology classes of psi, not by psi itself. Now about 4-point function. So is there a similar property for a whole? So let us try to formulate another lemma. So once again, so 4-point function depends only on cohomology class. So that would be like straightforward generalization. So now let us try to kind of prove this thing. So for a 4-point function, we don't have a single contribution. So we have these 3 contributions, and once again let us fix one of the contributions. So let us look at the amplitude for this case. So okay, so what we want to prove, okay, namely that here I have a Q of chi, and here I have like 3 other states, and this correlation of 3 other Q closed states, and then this 4-point function vanishes. So we can try to perform the same story. So let us choose my chi state to be like this state, and the rest of them are states like 1, 2, and 3. So then what we can do, we can once again play the same trick. so we can choose our, so that's where kind of this proposition that we can choose pairing freely. So let us choose pairing to be in this vertex. So then we can play the same trick. So we can move this orange Q through this pairing and apply it to other pair of edges. So therefore this diagram will equal to a sum of two contributions. Yellow vertex, and now kind of Q will be assigned to either of this internal edge or to this other, to a leaf number 3. So once again, because Q acting on psi k is 0, so this contribution would kind of immediately vanish, because here we got Q acting on one of the states that are Q closed. So what about this contribution? So here we have a different contribution because Q acting on some internal state. So let us look at a kind of algebraic presentation for this thing. So what we have? So we have. So let us compute this amplitude. So this amplitude equal to the following thing. So we have kind of mu3 0 in this vertex that pairs chi state psi 3. And then here it pairs with a Q acting on kind of kg minus of this product of state psi 1 and psi 2. So that is this amplitude. So now notice that Q doesn't quite annihilate this state. And it doesn't quite annihilate this state because we have this property that Q and K, they don't quite anti-commute. So there is some right-hand side, which is identity minus projective. So therefore, okay, let me temporarily erase this once and kind of continue performing this graphical manipulation. So what we will get? We will get the following thing. So here we have Q minus term, and using this property that Q and K anti-commute, we can express QK in terms of KQ and some additional one and project. So therefore this amplitude, when we commute this Q, we can draw this arrow by kg minus. So I can kind of commute through Q through kg minus, and I will get 3 contributions. So there will be a contribution like this. So it's kind of Q acting first, and then we act by kg minus. So here we have like Q kg minus, and here we have kg minus Q. Okay, and then there will be 2 more contributions. So let's depict them in the following way. So there will be a contribution with just G minus insertion. So that is from this identity contribution. That Q and K anti-commutes, we have 1, and here we just got G minus. And there will be another contribution with this kind of projector acting on G minus. So that are our 3 contributions which we generate from expressing QK as KQ plus identity point projector. So then once again, for this term, so here essentially Q acting on a product of 2 states. So therefore we can use Leibniz to essentially shift of action of this Q to either of the states 1 and 2, and this thing would vanish for the same reason as this diagram. Okay, so now we have this two leftover contributions. So this contribution is kind of easy to get rid because that was our property, our strange demand that G plus minus acting on V0 acting trivial. So that's kind of here what we have. So we have this V naught G minus. So first we okay. So then kind of depends on once again which order we read. So that essentially would be like G minus acting on V0, and that by assumption is 0. So that is one of the kind of part of the definition of HDQ. And so therefore what we left with this strange term, and this amplitude, this red amplitude equals to the following thing. So we have this V0. Let me even express mu 3 0. Let me rewrite it in terms of pairing. So that would be a pairing between, okay, with 1, 2, 3. So mu psi 3 and chi. That is our state chi. And here will be kind of we multiply these two states. Substitute the first argument in a pairing, and for a second argument of a pairing, we will apply G minus to this product of psi 1 and psi 2. And this thing is in general non-zero. So maybe our kind of lemma is not correct. That maybe we were too fast to generalize in this idea that correlation functions only depend on cohomology. However, lemma as formulated on a board indeed is not correct unless we make an additional assumption that G minus acting on all external states is also 0. So from our computation, it's not clear still how it will save us, because here we have G minus acting on product of states, and G minus does not obey Leibniz rule. So we can't just move this G minus through multiplication to act on argument. However, G minus obeys some other relation. So we have this strange relation that we wrote last time and kind of never finished to use. This is 7-term relation. And it turns out, I think I will just draw this. So let me draw this 7-term relation graphically. So graphically, the 7-term relation, let me use orange points. So what is the picture? So we have two incoming states. So we have a picture like this. So that is kind of combination of two multiplication, and then kind of left-hand side of this 7-term relation was like this. That first we multiply kind of states 1, 2, and then multiply again it with the state 3, and then act with G minus on the result of this kind of multiplication applied twice. And 7-term relation basically tells us that this expression equals to the following sum. So we have 7 pictures. Let me prepare these 7 pictures. Let me group them in two groups of 3. Once again, all pictures have like 3 inputs and a single output and 2 3 valence entities. And now we have different labels. So for these three pictures, we have G minus sitting this internal edge. And now we have three different labelings. So here, because this kind of multiplication was associative, gradient, commutative. So here, like different relabelings of 1, 2, and 3 would produce the same result. But now, due to application of G minus, it matters which state we multiply last. So therefore, there will be exactly three contributions, which are labeled by a choice of this last state. So 1, 3, 1. So that are three contributions, and similarly, the other three contributions, they are precisely contributions of this type. So here, once again, multiplication is commutative associative. So all three non-equivalent choices are essentially choices on which state kind of G minus acts. So here we can freely play with them. So that are three types of contributions. So either G minus acting on a product of two states, and there are exactly three choices, or G minus acting on one of the three states. So now what we have here, like this red expression that is non-zero, is essentially an expression where we take this diagram and kind of pair it, use different color. So essentially, I pair it with some additional state, fourth state. Sorry, my bad. So these three red pictures, they are essentially red pictures of this type that we take kind of output from these three pictures and pair it with the state form. So we introduce some two-valent vertex where we insert pairing, and the contribution from these three diagrams has this nice graphical presentation that exists three terms in seven-term relations. Seven-term relation pair it with kind of fourth state. Okay, so then seven-term relation tells us that this stuff that we get in our correlation function, because in correlation function we will have these contributions for three different labelings. So therefore we will have some of these contributions, like all states are even, so all signs will be plus. So therefore this red expression, which is sum of these three contributions, would be equal to this orange expression, which is sum of these four contributions. So here we apply pairing, kind of once again pairing with the fourth state at the very end. So we pair result of this payment term relation with the fourth. So here, due to this property that G minus of psi is 0, so each of these diagrams individually vanish because G minus acts on one of the states. And these three states will be precisely 1, 2, and 3 states. So here there would not be. Okay, sorry. We also assume that here we are shifted by Q exact state of a state that is G minus closed. Because among these states, in principle, we can encounter chi. So we can encounter either psi or chi. So, but all of them kind of vanish because G minus acts on one of the external states, and by assumption, all kind of 5 possible external states like four psi and chi, they are all G minus closed. And then what we left with a possible contribution when we kind of multiply three states. So we kind of multiply mu of some three states. I think in this case, like if we perform it carefully, it will be psi 1, psi 2, and then we multiply it with the state 3. So that is output, and then we add with G minus on this expression. And then what we do, we kind of perform a pairing of this thing with the fourth state. Which in this case would be chi. Okay, and then here we use our property that we can once again move G minus around for a pairing. So this expression would be equal to a G of this triple product. And here will be G minus applied to chi. And this thing is once again zero by kind of assumption of our lemma. Okay, so therefore, kind of 4-point function would depend on cohomology classes, given this additional property that all states and deformations of these states kind of G minus closed. So then we can naturally ask a question: what about 5 and higher point functions? Like going from 3-point function to a 4-point function kind of required us to kind of significantly modify our assumption by adding this additional assumption about G minus action. So it turns out that at higher point functions, this additional assumption, they just enough. So as long as we kind of assume that all our states are both Q closed and G minus closed, and we shift one of the states by Q exact of G minus closed element, so then the kind of amplitude, the correlation function, the endpoint correlation function is independent of such shift.
By our assumption, we only assume G minus Q chi is 0, which means
no. So here G minus chi. So we explicitly assume that we shift a state by G minus close, by Q of G minus close something, which is a stronger condition than this one. So this condition would imply that Q of G minus chi is 0. So sorry. Okay, Q and G minus anticommute, so Q of G minus chi is 0. But we additionally pose a stronger condition that not only Q of G minus chi is 0, but G minus chi itself is 0.
So what does it mean? We further assume the deformation is
so kind of to explain a kind of deep meaning of this property, we kind of need to either discuss kind of descendants on this formal level, or you need to wait till we get like some kind of explicit application of this lemma. So this lemma would be important when we will go from kind of HTQM description to Landau-Ginzburg-Saiter description. So in HTQM, like all the states psi, they are elements of some higher dimension of some infinite dimensional space. So which is space of differential forms on something. While in Landau-Ginzburg-Saiter theory, so we have like correlation function of phi's, which are essentially some much smaller space, the space of some holomorphic functions on something. And it turns out that we can realize holomorphic functions as a certain Q cohomology on this differential form. And then kind of to get from correlation functions in HTQM to correlation function on Dow Ginzburg side of theory, we will need to choose like some special representatives for cohomology classes that are essentially holomorphic functions of some space. But then kind of due to this additional assumption, we will need to explicitly check that the kind of difference between two representatives is indeed Q exact of G minus closed. So this thing would be important, and there will be some geometric meaning why it is G minus closed. But at this point, it's just some technical assumption to prove some.
It's like the whole definition is supported in like something like constant equivariant states.
So to get like some equivariance, we really need to go to descendants, and I don't want, because it's kind of will make things way more complicated. So yeah, so that is this additional nice property of endpoint correlation functions that given this additional assumption about G minus closeness, we essentially get kind of invariance of these correlation functions under the shift of our states by Q exact of G minus closed. Okay, so yeah, let me kind of briefly explain another property of amplitudes that will be essential for our proof of mirror symmetry, and which once again can be understood. Yeah, so to kind of formulate this property, let us define a kind of generating function for correlation function. So let us define universal state psi, which is sum over tk psi t. So here we once again will assume that all states psi has parity 0. So therefore these tk, they are just ordinary commuting formal variables. And formal variables in a sense that kind of all of them that all of them are nipotent. So okay, so we introduce this universal state psi, and then kind of if we look at correlation function with kind of n insertions of this universal state psi, so then due to this property, so this correlation function essentially equals to sorry. So let me here. So by definition, so when we have this correlation function psi1 to psi n, so it was sum over gamma, and here we sum it over all kind of possible permutations for assignment of this state. And because we sum it over all permutations, so this thing is manifestly symmetric in all arguments. So that is just a simple consequence of our definition.
Excuse me, tk squared equal to 0 seems to be the parity is 1.
No. So it just even important variables, like they're just variables for formal variables. So it's not realized as any kind of anti-commutative variable. Just for even variables, you can still assign this property. So that kind of just working over this formal variables. So we have like polynomial ring of over T1 to Tn quotient by n ideals generated by tk squared. So working over so therefore here, if I take endpoint function of this kind of generalized observable or generating observable, so what we will have here, we will have precisely, okay, so let's say that, yeah, that we have exactly n of them, so then it will be t1 to tk, and here will be precisely psi1 psi k, and there will be factor of n factorial. I think it's like this. So if I just substitute the sum of n terms and use the property that t squares to 0, so then the only terms that contribute is the terms when we have exactly one t, because we need n t's, and for n t's we without repeating tks we can choose them exactly once, but we can choose like each tk freely in arbitrary position. Like in a position 1 we can choose like any psi from 1 to n. In a position 2 we can choose any psi except psi that we choose in the first one. So therefore there will be totally n factorial terms. So therefore if I divide amplitude on the left over this n factorial, I will get a kind of n-point amplitudes with psi term.
It's n, not k. T1 to t.
Sorry, yes, you're so that sort of motivates for studying a new object, which is just this object. So we have like some number of psis. So in this case, let's say little n was equal to capital N, but as long as little n is no more than capital N, so we can study these objects and they are non-zero. So that's our kind of this amplitudes. And now let me introduce f, which is sum of these objects divided by n factorial. So I have like, and here n goes from 3 to infinity. So we know that so this sum is kind of will be always finite sum, because we have like finite number of original states, and therefore at some point when little n would be larger than capital N, like all these correlation functions would vanish because of this property tk squared today. So that is just some finite sum, and this finite sum essentially, if we expand it in the powers of t, would contain all kind of correlations, all possible correlation functions for this states of sum. So contains all correlation functions. So that is some nice generating function, and using this nice generating function, we can prove probably we will prove it next time. But let me at least formulate it. So now it will be theorem. That is rather non-trivial statement. So statement is the following. So this generating function would be a tool to prove it, but we can formulate it just in terms of correlation function. So suppose we have n+1 point correlation function of this n universal state psi and then some other additional state psi naught. So which is not among this sum, so some additional state. So then this object equal to the following thing. So this d over d epsilon equal to 0. And here it would be psi epsilon so that will be a derivative of n-point function in some deformed of n-point functions of some deformed states in a deformed HTQM. So this theorem it has this form. So kind of remark. Theorem has the same structure. As Landau-Ginzburg side recursion. So we can kind of recast the contact terms into deformation of phi's, and Landau-Ginzburg side recursion works exactly like this: that we choose one of the state phi, and then deform our states by a contact terms of states with additional phi, and then add an additional term which is derivative of kind of bracket in deformed theory. So to prove this theorem, we need we need some intermediate lemma that is actually very technical lemma, and there is not much inside. So let me just kind of give you without proof. So proof is written in our paper, and the idea is the following: that this kind of lemma about HTQM deformation. So HTQM is a collection of this data, which is a vector space Q, G plus minus, and G. That satisfies like all these nice properties that we discussed last time. So we can imagine studying family of HTQMs. And this family the kind of HTQMs in a family will have the same V, G plus minus multiplication and G, and the only thing that changes is Q. And this kind of Q epsilon in a family, it kind of starts with a Q plus some additional term in epsilon. And for this additional term in epsilon, we have the following construction. It is G minus of a multiplication by some state psi. So multiplication by a state psi naught can be treated as an operator on V. So kind of multiplication takes two vectors and produces third vector. But if we fix one vector to be psi naught, so then multiplication by psi naught is an operator. And okay, here I need to be careful. So psi naught is an even state. So multiplication by even state is an even operator. So therefore, to deform an odd operator Q, we take a commutator of this even operator G minus. So that will produce odd operators. This one is even, while this one will be odd, due to the fact that G minus is. And this kind of very technical lemma is basically like verifying all properties of HTQM for this kind of when we replace Q by a family of QX. So there is kind of one property that is sort of eliminated, and the rest of the properties they are just technical due to the fact that we define it our HTQM in rather technical way. So eliminating property is kind of to check that the family Q epsilon is a differential, or at least a differential in a linear order in epsilon. So when we square this expression, we would get kind of anti-commutator of Q with a commutator of G minus multiplication by a state psi naught. So then we will use a kind of graded Leibniz, graded Jacobi to rearrange this double supercommutator in a different way. And in this rearrangement, what we would have, I think in this rearrangement we would have like Q acting on psi naught, and here we will assume that our state psi naught is both Q and G minus closed. So as long as our state state psi naught is a Q and G minus closed, so then this property holds that the deformed state is indeed so deformed Q in linear order in epsilon is still a differential. So some other properties are kind of technical to verify, but for this property to hold, we need this additional assumption that psi naught is Q and G minus Q. So that gives us a kind of family of HTQMs parameterized by Q and G minus closed state psi. So here we once again assume that G minus of psi, G minus of psi naught is 0, and similarly Q of psi, Q of psi naught. So that gives us a kind of family of HTQMs in which we can compute amplitudes. And kind of the deformation of states, psi epsilon is once again psi plus epsilon, and here is the following thing: it is k G minus of mu of psi and psi. So that is deformation of states. So we essentially kind of multiply our state by psi naught. And then apply kg minus. So here there is once again some another consistency sublemma that q epsilon of psi epsilon is 0, because in order to kind of use some it's separate lemma, so it's not required for the proof of a theorem, but it's separate lemma that if we deform both q and psi in this way, then this kind of deformations preserve the property that if q psi and g minus psi were originally 0, then kind of in deformed theory, deformed psi will also q epsilon and g minus closed. So g minus closedness is kind of obvious because k commutes with g minus. So applying g minus to both sides of this relation, kind of here g minus acting on psi is 0 by definition of psi, and here g minus acting on this term is 0 because g minus commutes with k. and G minus square is 0. So that's why this property is kind of trivial, and this property requires kind of careful computation, but that is not surprising property, because kind of structure of acute deformation and structure of psi deformation kind of relies on multiplication with the state of psi naught. So it's kind of hardly surprising that these terms, linear terms in epsilon, would simply cancel out. Okay, and let me give a schematic proof of this theorem. Yeah, that would be the last thing that I do. So yes, it is kind of a bit sketchy, but I really want to get at least some sketchy proof of mirror relation. So I apologize for that. So for a proof, we notice the following thing, that if I have a tree, so I have a tree with n leaves, so then I can generate a tree with n plus 1 leaves by doing the following operation. So what I can do, I can attach an additional leaf to any of edges. So this operation is attachment of n plus 1, n plus first leaf to one of the edges. So that is kind of a way to generate all trees with n plus 1 leaves. So we start with all trees with n leaves, and then we kind of attach an additional leaf in all possible positions. So in such situation, we would typically get like some kind of overcounting, because like some trees with n plus 1 leaves can be constructed in multiple ways from attaching a leaf to that tree. And kind of that's where all our symmetry factors like n factorial and one of the automorphism of gamma, so they will save us from kind of overcounting. Yeah, and that's kind of the idea behind proving this theorem, that when we attach a leaf, so there are essentially two types of inequivalent situations. So let me draw them in my picture. So when I attach a leaf, I either attach it to external edge, like in this picture, or I attach it to one of the internal edges. So that's external edge. That is attaching to internal edge. So attaching leaf to external edge, so looks like some kind of deformation of this external state psi. So we have like state psi, and we have psi naught assigned to this additional leaf. So we can kind of look at this subtree as some kind of a new state generated by this attachment of u. And we can compute explicitly this subtree. So this subtree now it's not a number because it has kind of outgoing edge. So that will be like rather element of V, and this element of V is precisely multiplication of psi naught in this trivalent vertex, and then we need to apply propagator once. And that is precisely a kind of our structure for deformation of states. That the deformed states, it's just explicit evaluation of this leaf attaching to a state psi, treated as a deformed leaf of n-valid tree. So therefore we can kind of sum all kind of over all n+1 valent trees where we assign this additional state psi naught, assign it to kind of one of the external edges of original graph gamma. So the summation over amplitudes on such trees would be equivalent to summation over all amplitudes on original trees gamma n when we additionally deform our state by this additional term. So kind of in original graph we can either have like original state psi or one state that is kind of composite state obtained from kind of partially evaluating this leaf attachment to one of the edges. And once again, we are working in linear order in epsilon, so that's why if we formally kind of deform all states and keep only linear order, so the contribution would be given only by trees where only one leaf is deformed. So that will give us a kind of part of this expression when Q is undeformed and all psi's are deformed in this. And then similarly, when we attach a kind of a leaf to internal edge, so we can say that that we deform original propagator kg minus, we deform it to kg minus plus some additional construction which is kg minus of mu2 of psi 0, and here kg minus of the. So we start with a state, we apply kg minus multiplied by psi 0 and apply kg minus again. So instead of old propagator, which was kg minus, we kind of replace it by this picture, psi naught, and then here now we have two propagators. So that gives us a kind of a certain a certain deformation of a propagator. So attaching the leaf to internal edge gives us a deformation of propagator by this kind of multiplication of psi naught and additional kg minus. So then kind of there is an additional lemma that propagator constructed for this cube. So this Q epsilon defines an HTQM. So if it defines an HTQM, then we have a propagator defined for this cube. That propagator defined for this cube, or to be more precisely, K epsilon G minus, because additional G minus would kill some terms. So that will be precisely K G minus plus this expression. Okay, so K epsilon G minus equal to this expression. So that is kind of additional technical lemma that here we define this type of deformation, and the propagator for the deformation is kind of precisely equivalent to this operation of gluing in additional leaf psi naught to internal edge. And once again, we have like many internal edges, but because we are working only linear order in epsilon, so there is no problem in deforming each of the internal edges. So then kind of correlation function where all internal edges deformed in linear order in epsilon would be precisely given by a sum of the terms where we deform only one internal edge. And that would precisely correspond to all these situations when we get n plus first leaf as an attachment to internal edges of kind of tree with n leaves. So that is kind of schematic proof of that theorem. So unfortunately, like real proof is quite long. So probably it would like if properly written, it probably would take at least hour and a half. But I really want to reach tropical mirror theorem. So I gave the schematic proof. The kind of a full proof with all details carefully written in our second paper, which is tropical mirror symmetry correlation functions. So that is essentially a paper dedicated to studying properties of correlation functions, and we carefully prove this here. So I think I should really stop. I'm already very over time. Okay. Yeah, so sorry for going over time, but I really want to kind of prove this K properties. And I think next time, yeah, I think we only left with 2 lectures. So the plan is to spend this remaining 2 lectures in proving tropical mirror relation by relying on these preparational results that we have proven for a formal HTQM. And for a proof of tropical mirror symmetry, we will kind of apply these formal results to a very particular HTQM that we will first show that correlation functions in some particular HTQM equal to tropical Gromov-Ritt invariance. And then we will apply some of the formal results to amplitudes in this HTQM to get amplitudes in different HTQM, and then to kind of localize these amplitudes into correlation function Landau-Ginzburg cycles. So that would be like 3 steps in proving tropical mirror symmetry. So from Gromov-Ritt to HTQM, from one type of HTQM to another type of HTQM, then from second type of HTQM to Landau-Ginzburg cycle. So with these 3 steps and all these preparational results, we will just use them to kind of streamline the proofs of all this stuff. So it's several months of preparation to get the proof of tropical mirrors. But that's kind of how this complicated results work, that you need to first develop some proper technical tools, develop them formally, and then by applying them to a particular case, we will get a proof of some interesting statements. Okay, but hopefully these formal tools can be used in some other situations. So unfortunately, kind of Morse theory doesn't have this kind of graphs and vertices, so it makes the structure less interesting. So we still have like Q and G plus G minus, but kind of all our graphs, they're just lines with some marked points. So, but still there is some partial application of these tools to something outside of tropical medicine.
Okay, may I ask?
Yeah, quick.
It's okay. So these insertions, may I call it insertion? These insertions are on all of them are like equivalent. Lives like in infinity.
Yeah. So here we don't have any kind of operator insertions or observable like insertions that we had in tropical Gromov-Ritt theory. In tropical Gromov-Ritt theory, we have 2 types of objects. So we have like leaves of a tree which were associated to some compactifying divisors at infinity, and we have like some 2-valent vertices with insertions associated to choice of cycles, through which our curve passes. So in this construction, in this formal construction, so far we completely ignored this kind of marked points or 2-valent vertices. And next time we will see that this particular type of HTQM that we will use to describe tropical Gromov-Ritt invariance, it has some additional nice properties that do not follow from a general definition, such that we can essentially trade all kind of insertions into 2-valent vertices as a multiplication by a certain states.
States, you mean equivalent states?
Yeah. So they will. I'm not sure we call it equivalent, but they will be states which are Q and G minus closed. So they will be like action of these operators is kind of mu times some state dual to this operator, and this state would be this maximally nice state that it will be q and g minus closed. So therefore, like we can using this property, we can essentially turn any kind of amplitude relevant to Gromov-Witten theory into amplitude where we don't have any operator insertions and then just have some states on a list. But that is some special property that doesn't follow from this general algebraic definition of HTQM and only specific for Gromov-Witten theory.
Every marked point can be somehow surgery using a surgery to become three-valent.
So here we are working in kind of purely algebraic approach. So what we will see that that all these operators that are relevant for Gromov-Witten theory. So for Gromov-Witten theory, we will have like some cycle, tropical cycle, and kind of to get a Gromov-Witten invariant with this tropical cycle insertions, we will need to compute an amplitude with insertions of operator corresponding to this tropical cycle. And what we will show that this operator is actually mu2 by mu2 multiplication by some state that we can construct from this tropical insertion, and furthermore this state obeys this property is zero. So therefore we can essentially, without loss of generality, just remove all marked points and replace them by trivalent vertices with additional leaf marked by this tropical, by this psi gamma tropical, and then we will get like some real, and then we will use this formal theorems that we proved to kind of manipulate with these amplitudes.
So next time we will say the amplitude we construct today is like an A model.
No, so today we talked about kind of formal amplitudes as some algebraic object. So we just some numbers constructed in abstract HTQM. So next time we will start with this kind of proof that amplitudes in this particular HTQM equal to tropical Gromov-Witten invariant. And then when looking at amplitudes in this HTQM with kind of marked point and operators, we will see that these particular amplitudes have this additional nice property, so we can turn them into these correlation functions that we studied and proved some nice properties. So that would be our first step in proving of tropical mirror symmetry, and then next step would be some kind of relation between correlation functions in one theory and correlation functions in other theory, very much like relation like this, but it will be kind of slightly different relation. The number of observables wouldn't change, but size and q's would be different.
Yeah, so do we have something like WDV or some recursion relation other than this, like something like B-side recursion relation, not of visible side recursion relation? Do we have some A-side recursion relation in our example, in this particular example?
So yes, the answer is yes, that kind of you have a WDV type relation in kind of any formal HTQM. That in any formal HTQM, like I think I wrote like curly f, which was generating function for endpoint amplitudes, and then this curly f would satisfy WDV in a sense that third derivative with respect to t's would be just with some exchange would be equal to each other. So And this thing is kind of old result by Shadrin and Lossev. I think it's like 20-year-old result that they were interested in constructing new solutions to WDVV, and they found this nice way that given HQM data, you can construct a new solution, or you can construct a solution for WDV from this HQM data. And the proof, I think, is kind of somewhat similar to a proof that we had. So maybe just kind of leading coder term. So leading coder term in WDV is a situation that we kind of roughly multiply two 3-point amplitudes. So that is a leading term in third derivative. So here we can just write it like this as some kind of 4-point amplitude, where here instead of a propagator we just insert identity operator, identity on V. And then we can express our identity on V in the following way. So that it is projector plus anti-commutator of Q and K. And by doing this, sorry. Here, yeah, I think to get WDVV, yeah, it will be that. Okay, WDVV on cohomologous Q. So here would be projector, which is kind of 1 plus Q and K. And then the term where we have 1. So this term would be essentially kind of associativity property for some metum multiplication. So here we also have like sum of all 3 terms. So this one would be associativity. And this QK term would just vanish because we will either move 1Q to the left 2 states or 1Q to the right 2 states. So that is kind of simplest graphical proof of WDVV in their situation, and kind of they have a similar graphical argument for more general WDVV that essentially multiplying two kind of third derivatives is like drawing some tree with a pi naught insertion on one of the edges. Like instead of kg minus, we insert pi naught. And then we trade this pi naught into identity, and then with identity insertion we can rearrange our graph using associativity, and kind of the difference between pi naught and identity insertion is Q exact. So and then we kind of move Q like all the way to leaves, and all our states are Q closed. And the price for that would be generating some terms with G minus insertions, and these terms will be once again kind of cancelled due to this 7-term relation of G minus. So that is kind of essence of their proof of WDVV for H2. Maybe in their case, like one remark that I think they had like additional assumption that pi naught actually equals to the cohomology of Q. So in our assumption, pi naught contains